The universe is not an empty stage, but a living, breathing fabric. This hidden architecture of spacetime bends and warps under the weight of every star and planet. We often picture space as a passive void, a simple backdrop for the cosmic dance. But what if this fabric is the most active participant, the invisible hand shaping reality itself? By the end of this journey, you will see the cosmos through an entirely new lens, understanding how its geometry dictates everything from the orbit of a planet to the ultimate fate of all existence. We will uncover how a black hole can tear a hole in this fabric, and why the vacuum of empty space might hold the universe's deepest secret. What does it truly mean to live within a universe that is constantly remaking itself? Isaac Newton envisioned the cosmos as a grand, unchanging stage. On this fixed platform of absolute space and time, every event played out with clockwork predictability. An apple fell, planets traced their orbits, all governed by a force that reached mysteriously across the void. It was a powerful, intuitive picture, one that held for centuries. But then came Albert Einstein, who saw the stage itself beginning to move. He realized this rigid backdrop was not a passive arena at all. It was a dynamic, flexible fabric, a canvas that could stretch and warp. Picture a taut rubber sheet. Place a heavy bowling ball in its center, representing our sun. The sheet dips and curves under the weight, forming a deep, smooth well. Now roll a marble, our Earth, along this curved surface. It does not need a mysterious pull to guide it. It simply follows the natural contour of the indentation, tracing an orbit around the central mass. This is the heart of general relativity. Gravity is not a force in the traditional sense. It is the geometry of the stage itself. The sun does not reach out and grab the Earth. Instead, the sun's mass tells the fabric of spacetime how to curve, and the Earth simply follows the path of that curvature. This required a complete rewrite of the rules of geometry itself. For over 2,000 years, the flat, predictable world of Euclid dominated mathematics, with its parallel lines and perfect triangles. But to describe Einstein's warped universe, we needed a new language, the curved landscapes of Bernhard Riemann. In this new vision, the shortest distance between 2 points is rarely a straight line, and the angles of a triangle can add up to more than 180 degrees. This fundamental shift is captured in a simple yet profound statement. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. It is the first principle of the universe's hidden architecture, a cosmic dialogue between substance and shape. This cosmic dialogue between substance and shape is written in a precise mathematical language. At its heart lies a set of equations so powerful they can be written on a single line. G mu nu equals 8 pi gt mu nu over c to the fourth. Do not let the symbols intimidate you. This is the universe's blueprint, a set of instructions for how reality assembles itself. On one side of the equal sign, you have a description of the stage itself, the geometry of spacetime, its curves and its warps. On the other side, you have a complete inventory of everything on that stage, all the matter and energy that exists. The equation is a perfect balance. It declares with mathematical certainty that the shape of the cosmos is a direct and unavoidable consequence of the stuff within it. The presence of a single star, a wisp of gas, or even a beam of light commands the fabric of spacetime to bend in a specific way. Those other terms, the 8 pi, the capital G, and C, they are simply the conversion factors, the cosmic exchange rate that tells us exactly how much curvature a given amount of mass or energy will produce. This is the master rule of the hidden architecture. When we solve this equation for different scenarios, we unlock the universe's most incredible structures. The mathematics itself points the way to phenomena that defy our earthly intuition, leading us directly to one of its most astonishing predictions. Those elegant equations demanded a test, a way to prove that space itself could bend. The opportunity arrived with a total solar eclipse in the year 1919. British astronomer Arthur Eddington led an expedition to the island of Principe, off the coast of Africa. His goal was audacious: to see if the sun's gravity could deflect the light from distant stars. Think of it like this. You are looking at a street lamp through a perfectly flat pane of glass. The light travels in a straight line. But if that glass is warped like the bottom of a wine bottle, the path of the light bends and the lamp appears to be in a slightly different position. Einstein proposed that the sun acts like that warped glass. Its mass creates a dimple in spacetime, and any starlight passing close by must follow that curve. The shift would be tiny, almost imperceptible, but it was a definitive prediction. The challenge was that you could never see stars near the sun in the daytime. Their light is utterly washed out by the solar glare. The only chance was during the brief, eerie darkness of a total eclipse. On the day of the eclipse, the moon slid perfectly in front of the sun, revealing its shimmering corona. Eddington and his team hurriedly took photographs of the star field around the hidden sun. Later, they compared these positions to photographs of the same stars taken at night when the sun was nowhere near them. The result was unmistakable. The stars had shifted. Their positions were exactly as Einstein's theory had foretold, bent by the curvature of spacetime around our star. This was not light being pulled by a force. It was light traveling the straightest possible path through a warped universe. When the results were announced, Einstein became an overnight global sensation. It was the first direct proof that the fabric of the cosmos is not rigid but pliable, a dynamic entity that guides the journey of everything, even light itself. This single observation, the bending of starlight, opened a new window onto the cosmos. It showed that we could use these distortions as a cosmic tool, a lens to peer deeper into the universe than ever before. And if the gentle curve of a star could do this, what incredible vistas would open up when we looked at the most extreme warps in existence? Einstein's equations contained a second, even more startling prophecy. They revealed that spacetime is not a still canvas, but a dynamic membrane that can ripple. Imagine the surface of a still pond, suddenly disturbed by a skipping stone. Waves expand outward, traveling across the water. In the same way, when massive objects accelerate with incredible violence, they send shock waves through the fabric of the cosmos itself. Two black holes locked in a final, death spiral embrace do not simply merge in silence. As they whip around each other at nearly the speed of light, they churn the spacetime around them, generating waves that propagate outward in all directions. These are gravitational waves, a prediction Einstein himself made in 1916. Yet for a century, they remain just beyond our grasp, a ghostly whisper in the machinery of the universe. The problem was one of scale. By the time these ripples crossed the cosmos to reach us, their effect was almost unimaginably small. A passing gravitational wave would stretch and squeeze the very space we occupy, but by a distance far smaller than the width of a single proton. Detecting this was not a question of building a better telescope, but of constructing the most precise ruler ever conceived. That ruler finally arrived with LIGO, the Laser Interferometer Gravitational Wave Observatory. In September of 2015, after decades of searching, LIGO recorded a signal. It was not a flash of light or a burst of sound, but a precise wobble in the lasers within its 4-kilometer-long arms. The data was translated into a sound, a faint chirp that swept upward in frequency, the unmistakable signature of two black holes, each about 30 times the mass of our Sun, completing their final orbits and merging into one. That chirp had been traveling for over 1 billion years before it gently stretched and compressed our planet. Think about what that means. We did not see this event. We felt it. We measured the literal flexing of spacetime itself. This was a direct confirmation that the universe's architecture is not just curved, but elastic and alive, ringing like a cosmic bell. These ripples carry the pure, unvarnished story of the most violent events in the universe, from colliding neutron stars to the birth of black holes. They are a new sense for humanity, allowing us to listen to the hidden vibrations of reality. And if space-time can ripple, what other hidden movements are waiting to be felt? The silent ringing of that cosmic bell reminds us that space-time is not a passive stage, but an active participant shaped by its contents. To truly grasp this hidden architecture, we must examine the tools available to the cosmic architect. The blueprint, Einstein's equation, is explicit about what molds the fabric. It is not just mass, it is everything. Mass, energy, and momentum are the fundamental chisels that carve the curves of reality. They are not entirely separate things, but different expressions of a single, profound quantity. This is the heart of Einstein's legendary equation, E equals mc squared. It tells us that energy and mass are two sides of the same coin, convertible and equivalent. A dying star with its immense mass warps spacetime profoundly. But consider a simple, perfectly mirrored box, empty but for a single beam of light bouncing back and forth between its walls. Those photons are massless particles of pure energy, yet as they ricochet, they carry momentum and exert a tiny pressure on the box's walls. According to the equations, this entire system, this box of light, now possesses a gravitational field. It curves the spacetime around it. Even the internal pressures and stresses within a star, the immense forces fighting gravity's inward crush, contribute to the overall command it gives to the cosmic fabric. All of these influences, mass, energy, momentum, pressure, are woven together into a single mathematical entity called the Stress-Energy Tensor. This is the complete and total inventory that tells spacetime exactly how to curve. It is a profoundly democratic process, the nuclear furnace at the heart of a galaxy, the silent warmth of a rock absorbing sunlight, and the intangible light streaming from a distant quasar, all of them, without exception, leave their unique imprint on the geometry of the universe. Every form of existence is an architect contributing to the grand design, and when we follow this principle to its most extreme conclusion, we arrive at the universe's ultimate sculptors, entities that wield these tools with such overwhelming force that they tear the fabric of reality itself. These ultimate sculptors are black holes, where the dialogue between matter and geometry reaches its final, silent conclusion. If the sun's gravity creates a gentle dimple in the cosmic fabric, a black hole is a puncture, a bottomless pit where spacetime curves back on itself completely. This extraordinary object begins with the death of a massive star. When such a star exhausts its nuclear fuel, the outward pressure that once supported it vanishes. With nothing to resist it, the star's own immense gravity causes a catastrophic collapse. The entire mass, often several times that of our Sun, is crushed inward toward an infinitely small point. The density becomes so overwhelming that spacetime warps into a perfect trap. It folds over itself, creating a one-way boundary called the event horizon. Think of it as the cosmic point of no return, a waterfall's edge in the river of space. Anything that crosses this threshold, from a stray atom to a beam of light itself, is lost forever to our universe. It cannot reverse its course, not because it is being pulled, but because all paths within that warped geometry lead inexorably inward. Inside this boundary, at the very heart of the black hole, lies the singularity. This is a point where our current understanding of physics simply shatters. According to the equations, matter is compressed to infinite density, and the curvature of spacetime becomes infinite. The rules of general relativity, which have guided us so far, break down completely. It is a realm where the very concepts of space and time cease to have any meaning we would recognize. Yet for all the chaos at its core, a black hole is paradoxically a thing of stark simplicity. It has been famously said that black holes have no hair. This whimsical phrase means that a black hole is stripped of all complexity. It remembers almost nothing of the star that formed it, of the planets it may have consumed, or the intricate structure of the matter that fell in. All that remains are three bare properties: its mass, its spin, and its electric charge. These three numbers define everything about the gravitational field it produces, defining the entire architecture of the whole and the empty space around it. This makes a black hole perhaps the most perfect and simple object in the entire universe, a pure manifestation of spacetime geometry. They are not the ravenous cosmic vacuum cleaners of popular fiction, blindly sucking in everything from afar. Their gravitational pull at a distance is just like that of any other object of the same mass. If our sun were instantly replaced by a black hole of the same mass, the Earth would continue to orbit in complete darkness, held in the same gravitational grip. A black hole's power is not in its reach, but in the ultimate nature of its boundary, the event horizon. It is the final and most extreme laboratory for testing the limits of Einstein's theory. By studying these perfect pits in reality, we are forced to ask what happens when geometry becomes so extreme that it swallows the very rules that created it. The stark simplicity of a black hole stands in sharp contrast to another fantastical structure hidden within the mathematics of relativity. The very same equations that predict those perfect gravitational pits also allow for cosmic shortcuts, theoretical tunnels known as wormholes. Imagine our warped rubber sheet of spacetime, but now picture two distant points being connected not by a long, curved path across the surface, but by a tight handle that bridges the gap from underneath. This is the essence of a wormhole, a shortcut through the folded fabric of the cosmos. In theory, such a structure could connect two vastly distant regions of our universe, or even serve as a gateway to an entirely different cosmos altogether. The entrance of a wormhole might appear as a spherical portal, a region of space that looks much like a black hole from the outside, but with one crucial difference. Instead of leading to a crushing singularity of no return, it would open into a tunnel, a throat that guides you to another place and time. Yet this incredible promise comes with a profound catch. The equations show that such a tunnel would be catastrophically unstable. The moment it forms, the gravitational forces within would snap it shut, collapsing the passage faster than even a beam of light could traverse it. To hold this cosmic doorway open, to make it traversable for anything, you would need a counterintuitive kind of scaffolding. You would need a substance that generates a gravitational repulsion, something that pushes spacetime apart instead of pulling it together. This hypothetical material is often called exotic matter, a substance with negative energy density. While certain subtle quantum effects hint that negative energy might be possible in microscopic amounts, whether it can exist in the vast, stable quantities needed to prop open a cosmic freeway remains one of physics' greatest unanswered questions. For now, wormholes exist firmly in the realm of mathematical possibility and science fiction. They are not observed phenomena, but tantalizing suggestions written in the universe's own blueprints. Their potential existence forces us to confront the deepest questions about reality. If space-time can be punctured and threaded in this way, then the universe's architecture is not just warped, but potentially riddled with hidden connections, a labyrinthine structure far beyond our current perception. To understand if such a thing could ever be real, we must look beyond the smooth curves of relativity and into the chaotic, probabilistic world of the very small. But the perfect geometric simplicity of a black hole or a wormhole hides a deep crack in our understanding of physics. We have two master theories, each incredibly successful in its own domain, yet they speak completely different languages and refuse to be reconciled. General relativity describes the cosmos on its largest scales, a world of smooth, continuous curves and deterministic geometry. It is a theory of the certain, the predictable. Quantum mechanics, however, governs the realm of the atom, a world of probability, uncertainty, and discrete jumps. Here, particles pop in and out of existence, and reality is fundamentally fuzzy. This creates a monumental conflict when we try to describe the center of a black hole or the first moment of the Big Bang, places where immense gravity meets the subatomic scale. In these extreme environments, the equations of general relativity break down, yielding nonsensical answers like infinities. This tells us that our picture of a smooth, continuous spacetime is likely an illusion, a convenient approximation that works well for our human-scale world but fails utterly at the foundation of reality. The quest to unite these two pillars of physics forces us to ask a startling question. Is the fabric of the universe itself woven from something more fundamental? Could spacetime have a granular, pixelated structure when we examine it closely enough? One compelling answer comes from a theory known as loop quantum gravity. It proposes that space is not a smooth continuum. Instead, it is woven from a network of tiny, one-dimensional loops. These loops are incredibly small, existing at the Planck scale, a size so minuscule that comparing an atom to the entire solar system would still not capture how tiny it is. In this view, space is composed of a finite number of these loops, intersecting to form a fabric of space itself. This means that area and volume are not continuous quantities that can be divided forever. They come in discrete, indivisible units, much like the pixels on your screen. From a distance, a digital image looks perfectly smooth and continuous, but zoom in far enough and you will see the individual blocks that construct the whole picture. Loop quantum gravity suggests that the universe operates on a similar principle. The smooth, warping stage of general relativity is an emergent property, a large-scale average of a vast number of tiny, quantized grains of space. This has a profound implication for the fate of singularities. In the heart of a black hole, general relativity predicts matter is crushed to an infinitely dense point where space-time curvature becomes infinite. But in loop quantum gravity, because space is granular, there is a smallest possible volume. Matter cannot be compressed beyond this limit. The result is not a singularity, but a bounce. The crushing collapse of a dying star could rebound, spewing its material back out into a new region of spacetime. This idea even applies to the birth of our entire cosmos, suggesting the Big Bang was not a true beginning from nothing, but a great bounce from a previous universe that had contracted. The quest to see this granular structure of spacetime is perhaps the greatest experimental challenge in all of physics. These grains of space are so unimaginably small that directly observing them is far beyond our current technology. Yet, scientists are searching for indirect clues. They analyze the light from the most distant gamma-ray bursts, looking for subtle signs that the energy of these photons has been slightly altered by bumping against the pixelated structure of spacetime on its billion-year journey. They listen to the ringing of spacetime from gravitational waves, searching for faint echoes that might betray a granular foundation. We are, in effect, trying to read the universe's source code by studying the behavior of the reality it renders. Uncovering this hidden grain would be the ultimate discovery, revealing that the stage itself is built from something deeper and forcing us to rewrite the story of cosmic architecture from its very first line. This granular view of space forces us to confront an even more radical possibility. What if the universe's three-dimensional richness is merely a projection, a grand illusion? The holographic principle proposes exactly that, suggesting our reality is a cosmic hologram. The idea finds its roots in the puzzling nature of black holes. When an object falls into a black hole, it vanishes behind the event horizon, seemingly lost forever. This presents a paradox because the laws of quantum mechanics insist that information can never be truly destroyed. So where does the information go? The startling resolution is that it does not fall in at all, at least not in the way we think. The holographic principle states that all the information describing the object, every detail of its atoms and their arrangement, is encoded on the two-dimensional surface of the event horizon itself. It is painted there like a fantastically complex and microscopic fresco. The three-dimensional object we see falling in is, in a profound sense, just a translation of that two-dimensional data. Think of a credit card hologram. The flat, shiny sticker holds all the information needed to project a three-dimensional image that seems to float in space. The holographic principle argues our universe operates on a similar, though vastly more complex, scale. The entire volume of space inside a region, with all its stars, planets, and the fabric of spacetime itself, could be a projection from information stored on a distant, surrounding boundary. This turns our intuition inside out. We perceive ourselves living within a three-dimensional world, but according to this idea, the true reality is the two-dimensional data encoded on the cosmic shell that contains us. The solidity of the desk in front of you, the vast depth of the night sky, all of it might be emergent, a consequence of information processing happening on a lower dimensional surface we cannot see. This blurs the very line between the universe's architecture and its blueprint. The curved spacetime of general relativity is no longer the foundational layer. Instead, it is a secondary effect, a holographic projection arising from a more fundamental, information-theoretic structure. The universe is not built from tiny grains of space, but from bits of information. Its laws are not the laws of geometry, but the laws of computation. If this is true, then the deepest secret of the cosmos is not a force or a particle, but a code. And we are living inside its magnificent rendering. This hidden cosmic code is written on a universe that is not static, but actively evolving. For most of the 20th century, astronomers believed that the expansion of the cosmos, set in motion by the Big Bang, was gradually slowing down. The collective gravity of all the galaxies, all the stars, all the dark matter, was thought to be pulling on the fabric of space-time, applying a cosmic brake to its outward flight. Then, in the late 1990s, two independent teams set out to measure this deceleration by studying distant stellar explosions. They used Type 1, a supernova, which have a known intrinsic brightness as cosmic mileposts. By observing how much dimmer these explosions appeared from Earth, they could calculate their distance. By measuring how much their light was stretched to the red end of the spectrum, they could determine how much the universe had expanded since the blast occurred. The results were not just surprising, they were revolutionary. The most distant supernova were significantly fainter than they should have been. This meant they were farther away than anyone had predicted. The only possible explanation was that the expansion of the universe was not slowing down at all. It was speeding up. Some mysterious, repulsive force was stretching the cosmic fabric itself, pushing galaxies apart at an ever-increasing rate. This discovery was so shocking it required a complete rewrite of our cosmic story. The driving force behind this runaway expansion was given a name: dark energy. It behaves like a kind of anti-gravity, a uniform energy density inherent to the vacuum of empty space itself. Think of the universe as a loaf of raisin bread baking in an oven. The raisins are galaxies, and the dough is the fabric of spacetime. If the dough is simply rising, the raisins move apart, but at a steady pace. Dark energy is like yeast suddenly becoming hyperactive, causing the dough to inflate faster and faster, stretching the space between every raisin at an accelerating rate. This effect is written into Einstein's own equations as a possible term, the cosmological constant. It represents a constant energy density of the vacuum, a gentle pressure that pushes spacetime apart. For decades, Einstein considered this his greatest blunder, introducing it to force a static universe and then discarding it when the expansion was discovered. Now it seems he may have been right for the wrong reason. This repulsive force is not just a small effect. Measurements show that dark energy constitutes about 68% of the total energy content of the universe. It is the dominant component of reality, the primary architect shaping the large-scale geometry of the cosmos. Yet, its fundamental nature remains one of physics' greatest enigmas. We see its effect with absolute clarity, a force that is actively stretching the very stage we stand on. But we have no idea what it actually is. Is it truly a constant property of empty space, or is it a dynamic field that could change over time? The answer will determine the ultimate fate of everything, a final, silent chapter written by the hidden hand of the universe's architecture. While dark energy pushes the cosmos apart on the grandest scales, a second, equally mysterious force works in opposition, pulling the universe together. This is dark matter, the invisible scaffolding that holds galaxies intact. We have never seen a single particle of it. It does not glow, it does not shine, and it does not cast a shadow. It is completely transparent to light. So how can we be so sure it is even there? The evidence comes from watching how things move. In the 1970s, astronomer Vera Rubin was studying the rotation of spiral galaxies. She expected stars on the outer edges, far from the bright galactic core, to orbit more slowly, just as Pluto, at the edge of our solar system, moves much more sluggishly than Mercury close to the Sun. But her observations revealed something astonishing. The stars on the outskirts were orbiting just as fast as those near the center. It was as if the entire galaxy was embedded within an enormous, invisible sphere of mass, a halo of something that was tugging on those outer stars, keeping them from flying off into the void. This something was dark matter. Its gravitational influence is the only thing preventing galaxies from tearing themselves apart. We see this cosmic scaffolding at work in other ways, too. When we look at massive galaxy clusters, we often see distant galaxies behind them, their light warped and stretched into faint, luminous arcs. This is gravitational lensing, the same bending of light that Eddington observed, but on a colossal scale. The amount of bending is far too severe to be caused by the visible stars and gas alone. There must be an immense amount of unseen mass warping the spacetime in that region, a hidden gravitational lens sculpted by dark matter. This invisible substance is not a small component of the universe. For every ounce of ordinary matter, the atoms that make up stars, planets, and us, there is about 5 times more dark matter. It forms a vast cosmic skeleton, a framework upon which the luminous galaxies are draped. Without this unseen anchor, the universe would look utterly different. Galaxies would never have clumped together in the early cosmos. and the great cosmic web of filaments and voids would never have formed. Dark matter is the great architect of structure, the silent, gravitational hand that carved the universe from a formless cloud into the magnificent tapestry we see today. Yet its true identity remains one of science's most profound puzzles. We can map its gravitational shadow with exquisite detail. We can feel its pull on the fabric of spacetime, but we still do not know what it is made of. The silent architecture of dark matter finds its origin in the universe's first breath. To understand how spacetime shaped everything we see, we must look back to its earliest moments, to a time before the first stars ignited. Our most powerful window into that era is the cosmic microwave background, a faint glow that permeates all of space. This is the afterglow of the Big Bang itself, a fossilized snapshot of the cosmos when it was a mere 380,000 years old. Before this moment, the universe was a searing, opaque plasma, so dense that light could not travel freely. Particles of light, photons, were constantly scattered by a thick fog of electrons. But as the universe expanded and cooled, electrons and protons combined to form the first neutral atoms. In that instant, the cosmic fog lifted. The photons, finally set free, began a journey across the universe that continues to this day. We detect that ancient light now as a uniform microwave signal, cooled by expansion to just a few degrees above absolute zero. Yet this background is not perfectly smooth. When we examine it with incredibly sensitive instruments like the Planck satellite, we see a mottled sky, a tapestry of minute temperature variations. Some patches are ever so slightly warmer, others infinitesimally cooler. These tiny fluctuations, mere millionths of a degree, are the most important imprints in the cosmos. They are the fossilized echoes of quantum fluctuations that rippled through the primordial fabric of spacetime itself. In the first fraction of a second after the Big Bang, the vacuum of space is thought to have undergone a period of hyper-expansion called inflation. During this burst, microscopic quantum jitters, the inherent fuzziness of the infant universe, were stretched to cosmic proportions. These jitters became slight differences in density, tiny hills and valleys in the gravitational landscape of the young cosmos. Where the density was marginally higher, gravity had a stronger grip. Over billions of years, these spots acted as seeds, pulling in more and more dark matter and gas. The slightly warmer spots in the cosmic microwave background correspond to these primordial gravitational wells, the regions that would eventually collapse under their own weight to form the first galaxies, the great clusters, and the vast cosmic web. The cooler spots became the great cosmic voids. By meticulously mapping the patterns in this ancient light, cosmologists are essentially reading the universe's initial conditions. The precise statistics of these hot and cold spots tell us about the geometry of the cosmos, its total content of matter and energy, and even the properties of the inflationary epoch that set it all in motion. This faint microwave whisper is our most direct connection to the infant universe, a baby picture that reveals how the hidden architecture of spacetime wrote the blueprint for all of existence. This remarkable uniformity, the smooth cosmic canvas we observe across billions of light years, presented a deep mystery. Why does the universe look so similar in every direction? The answer lies in a breathtaking event from its first moments, a period of hyper-expansion known as cosmic inflation. In the tiniest sliver of a second after the Big Bang, the universe did not just expand, it exploded in size, doubling its dimensions again and again in an exponential runaway. The entire observable cosmos was stretched from a subatomic speck to a volume larger than our entire solar system, all in a span of time so brief it defies comprehension. This violent, explosive growth acted like a cosmic iron, relentlessly smoothing out the fabric of spacetime. Any primordial wrinkles, any large-scale lumps or twists in the early universe were stretched so thin they became imperceptible. This is why the temperature of the cosmic microwave background is so incredibly even from one patch of sky to another. The universe was ironed flat, its geometry set on a vast, uniform scale. But inflation did more than just smooth the cosmos. It also created the seeds for all future structure. In that seething, quantum froth of the infant universe, tiny fluctuations were an inherent part of reality. Virtual particles flickered in and out of existence, creating microscopic hills and valleys in the energy field. Under normal circumstances, these quantum jitters would be insignificant, vanishing almost as quickly as they appeared. But inflation seized upon these tiny imperfections and magnified them to a cosmic scale. As spacetime stretched at a dizzying rate, it locked these quantum fluctuations in place, stretching them from the subatomic world to sizes of entire galaxies. These magnified ripples in density became the gravitational seeds, the slight over-densities that would, over billions of years, pull in dark matter and gas to form the first stars, the galaxies, and the great cosmic web we see today. Without this initial stretch, the universe would be a far different place, perhaps a formless, barren void without any structure at all. The theory of inflation is now a cornerstone of our cosmic story, explaining both the stunning large-scale smoothness and the origin of all cosmic structure in one elegant, powerful mechanism. It describes the pivotal moment when the fundamental architecture of spacetime was set, a brief, violent burst that dictated the fate of everything to come. Why does time flow in only one direction? The universe seems to run on an irreversible clock where we vividly remember the past but can only guess at the future. This one-way street, known as the arrow of time, is not just a feature of our minds but is etched into the geometry of spacetime itself. At the heart of this mystery lies a concept called entropy, a measure of disorder. The second law of thermodynamics is simple and unforgiving. It states that the total entropy of the universe always increases. A shattered glass does not spontaneously reassemble, and smoke never flows back into a cigarette. Things move from order to disorder, and that progression gives time its apparent direction. But why does this law exist? The answer lies in the universe's first moment. The Big Bang did not begin with chaos, but with a state of incredibly low entropy, a condition of exquisite and improbable order. The universe was a near-perfect, uniform soup of hot, dense energy. This was the ultimate wound-up spring, the single, low-entropy starting point from which everything has since unwound. As the cosmos expanded and cooled, that initial order began to dissolve, and entropy started its inevitable climb. This is the foundational reason we have a past and a future that look so different. Yet the story of increasing disorder is not as straightforward as it seems. In our daily lives, we see order collapse into chaos, but on a cosmic scale, gravity is a master of creating order from disorder. A formless cloud of gas will collapse under its own gravity to form a brilliant, structured star. This seems like a decrease in entropy, a move toward order. How does that fit the rule? The key is to understand gravitational entropy. When a star forms, the energy that was once spread evenly throughout a vast cloud of gas becomes concentrated and organized. But in the process, it generates immense heat and light, radiating disorder out into the universe. The overall entropy of the cosmos still increases dramatically, even as local pockets of stunning order emerge. This gravitational clumping, the very process that builds galaxies and stars, is one of the primary engines driving the universe's total entropy upward. The large-scale geometry of the cosmos, its relentless expansion fueled by dark energy, provides the stage for this grand unfolding. In a static, unchanging universe, time might not have a clear direction. But our universe is stretching, creating ever more space, and with it, ever more possible states for matter and energy to occupy. This constant opening of new possibilities is what allows entropy to forever increase, ensuring the arrow of time flies relentlessly forward. The very shape of reality, from its smooth beginning to its accelerating expansion, may be the ultimate reason we experience a past that is fixed and a future that is open, a silent testament to how spacetime's architecture writes the rules of time itself. This subtle warping of spacetime, first glimpsed during a solar eclipse, has evolved into one of astronomy's most powerful tools. Gravitational lensing turns the universe itself into a colossal telescope. When light from a tremendously distant galaxy travels across the cosmos, its path is not always straight. If its journey brings it close to a massive foreground object, like a dense cluster of galaxies, the fabric of spacetime it must traverse is deeply curved. The light follows this curvature, bending around the obstacle. From our vantage point, this cosmic mirage can produce spectacular effects. The single, faint background galaxy might appear to us as multiple, distorted images arrayed around the central cluster. In a perfect alignment where the source, the lens, and our telescope are in a straight line, the light can be smeared into a complete circle of fire, a shimmering halo known as an Einstein ring. These are not new objects being created, but a single reality being remapped by the geometry of spacetime itself. For astronomers, this is a gift. That distant galaxy, which would normally be a faint, unresolved speck, is magnified and brightened by this natural lens. It allows us to peer deeper into the cosmos than any human-made telescope could ever manage, studying the formation of the very first galaxies. But the true power of this tool goes beyond mere magnification. By carefully measuring the exact shape and distortion of these cosmic mirages, scientists can perform a kind of cosmic tomography. They can map the precise distribution of mass within the lensing cluster. The stunning result is that the visible galaxies in the cluster contribute only a small fraction of the warping we observe. The majority of the lensing effect is caused by the immense, invisible halo of dark matter enveloping the entire cluster. By watching how light bends, we are not just seeing distant objects, we are tracing the outline of the invisible scaffolding that holds the universe together. The cosmos has handed us a lens crafted from its own hidden architecture to illuminate its deepest secrets. Our planet is not just a mass that warps space, it is a spinning top that pulls the fabric of reality along with it. This subtle phenomenon is called frame dragging. Imagine a child spinning a ball in a jar of thick honey. As the ball turns, it does not move in isolation. It drags the surrounding honey into a slow, swirling motion. In the same way, a rotating planet like Earth twists the invisible threads of spacetime around itself. The effect is incredibly faint, but it is real. To prove it, scientists launched the Gravity Probe B satellite, a marvel of precision engineering. It carried gyroscopes so perfectly spherical, they were considered the roundest human-made objects in existence. In orbit, free from atmospheric drag, these gyroscopes were designed to point at a distant guide star. If spacetime were perfectly still, their orientation would never change. But it did. The spin of our planet ever so gently tugged on the fabric of spacetime, causing the gyroscope's axis to drift minutely over time, exactly as predicted. This confirmed that mass does not just tell spacetime how to curve, motion tells it how to swirl. Now, amplify this effect from a gentle tug to a cosmic whirlpool. Around a rapidly spinning black hole, frame dragging becomes so violent it creates a region called the ergosphere, a boundary outside the event horizon itself. Here, spacetime is dragged around at such a ferocious pace that it becomes impossible to stand still. No matter how powerful your rockets, you would be swept along in a torrent of rotating geometry, forced to move with the flow of space and time itself. This is not a force acting on you, it is the very stage beneath your feet turning into a carousel from which there is no disembarking. The universe is not a static set, but a fluid, dynamic entity that can be set into motion, proving that the hidden architecture is not just shaped but stirred. Our universe's unique set of laws might be nothing more than a local ordinance. This startling idea emerges from the same physics that gave us cosmic inflation, the violent stretching that smoothed and seeded our early cosmos. According to the theory of eternal inflation, that explosive expansion never truly stopped. Instead, it continues eternally in a background sea of hyper-stretching spacetime. But within that sea, in random locations, the inflationary energy decays, like bubbles forming in a pot of boiling water. Each of these bubbles is a universe pinching off from the inflating background and expanding at its own pace with its own properties. Inside one such bubble, the inflationary energy transformed into the hot soup of particles that became our cosmos. But the process suggests there could be an endless froth of other bubbles, a vast multiverse where each universe is a separate domain with its own random selection of physical constants. In one bubble, the strength of gravity might be 10 times stronger, making stars burn out in a cosmic blink. In another, the cosmological constant could be so large that matter is ripped apart before it can ever form a single atom. Some universes might have 4 dimensions of space, rendering our familiar 3-dimensional geometry quaintly provincial. Others might not support complex chemistry at all, remaining dark and barren for eternity. Our universe appears finely tuned for life not because of a grand designer, but simply because we are here to observe it. In an infinite ensemble of possibilities, a universe that allows for galaxies, planets, and conscious observers was bound to appear somewhere. This is the Anthropic Principle in a multiverse context, a statistical selection effect rather than a fundamental law. While this idea is currently beyond the reach of direct experimental proof, it represents a profound shift in our understanding of cosmic architecture. The rules we once thought were universal and absolute, the bedrock equations of physics, might merely be the provincial bylaws of our particular cosmic neighborhood. The true fundamental reality could be a landscape of unimaginable variety, a cosmic metropolis where our entire history is just one quiet street in an infinite city. Our comfortable 4-dimensional reality might be a profound illusion. We move through 3 dimensions of space and 1 of time, but the deepest laws of physics hint that this is merely the surface level of existence. Imagine, if you can, a garden hose stretched across a vast field. From a distance, it appears as a single line, a one-dimensional object. But if you were an ant crawling on its surface, you would discover a second dimension, the circular path around its tube. The hose has a long, extended dimension we can see from afar, and a tiny, curled-up dimension that only becomes apparent upon close inspection. Some of the most ambitious theories in physics propose that our entire universe is like that hose. The 3 spacious dimensions we know could be the large, extended ones, while there may be 6 or 7 additional spatial dimensions, curled up into shapes so fantastically small that they are completely hidden from our everyday perception. These dimensions are not empty voids waiting to be filled. They are part of the very fabric of reality, twisted into intricate geometric shapes at the Planck scale. This is a core idea of string theory, a framework that attempts to sew together the torn fabric of general relativity and quantum mechanics. In this view, the fundamental constituents of the universe are not point-like particles, but unimaginably tiny, vibrating loops of energy strings. And just as the vibrations of a guitar string determine whether it plays a C note or a G note, the specific vibrational patterns of these fundamental strings determine the properties of every particle in existence, from electrons to quarks. But here is the crucial part: the possible vibrational patterns are not arbitrary. They are dictated by the exact geometry of those hidden, curled-up dimensions. The shape of this hidden landscape determines the laws of physics in our visible universe. The number of particle families, the masses of particles, even the strength of the fundamental forces, could all be frozen accidents of this multidimensional geometry. This offers a potential solution to one of physics' greatest puzzles, the puzzling weakness of gravity. Gravity is astronomically feebler than the other forces, the electromagnetic force and the nuclear forces. Why? The answer might be that gravity is not confined to our four-dimensional sheet of spacetime like the other forces are. While electromagnetism is stuck to our four-dimensional brain, as theorists call it, gravity, which is the geometry of spacetime itself, can leak out. It can spread its influence into all the extra dimensions, diluting its strength from our perspective. The force that holds entire galaxies together appears weak to us because most of its true power is flowing into realms we cannot see. This suggests that the true, fundamental architecture of everything is a vibrant, multidimensional reality, a cosmic symphony playing out in 10 or 11 dimensions. The universe we perceive is just a four-dimensional shadow, a slice of a far richer and more complex whole. This conflict between the two pillars of physics comes to a head in the black hole information paradox. On one hand, general relativity presents a stark and simple picture. When a book, a star, or an entire spaceship crosses the event horizon, it is gone. Its immense mass and energy are added to the black hole, but all the intricate details, the specific arrangement of atoms that made it a book, a star, or a spaceship, are seemingly crushed out of existence at the singularity. The information that defined that object is permanently erased from our universe. For relativity, this is a feature, not a bug, a finality written into the geometry of spacetime itself. Yet quantum mechanics declares this to be impossible. In the quantum world, information is sacred. It can be scrambled, it can be hidden, but it can never be truly annihilated. If you could somehow reverse all the motions of every particle in a cloud of smoke, you could, in principle, reassemble the original cigarette. The laws of quantum physics are reversible, preserving the complete history of every interaction. The idea that a black hole could be a cosmic shredder, permanently destroying this information, strikes at the very heart of quantum theory. So who is right? Does the hidden architecture of spacetime contain a fundamental flaw, a place where its geometry simply overwrites the quantum rules? The most promising answer suggests the information is not lost at all, but preserved in a way we are only beginning to understand. Stephen Hawking's own work provides a clue. He realized that black holes are not perfectly black. Due to subtle quantum effects at the very edge of the event horizon, they slowly evaporate, emitting a faint glow of particles now known as Hawking radiation. Initially, Hawking believed this radiation was purely thermal, a random hiss carrying no information about what fell in. If this were the case, then once the black hole completely evaporates, all the information it ever consumed would indeed be lost forever. This is the paradox in its purest form, but later many physicists, including Hawking himself, came to suspect that the radiation is not completely random. The information about the fallen book might be imprinted onto this Hawking radiation, slowly and chaotically leaking back out into the universe over the black hole's immense lifetime. It would be like burning a book. The pages are turned to ash and smoke, seemingly destroying the story. But if you had a perfect, impossibly powerful microscope, you could, in theory, analyze the precise arrangement of the smoke particles and the chemical composition of the ash to reconstruct every single word. The information was never gone, it was just transformed into an incredibly complex state. In the black hole version, the event horizon itself acts as a chaotic encoder, scrambling the information and radiating it back out. This points toward a resolution where the principles of quantum mechanics ultimately prevail, and the smooth geometric picture of a black hole must be revised. The event horizon may not be the calm, one-way membrane of relativity, but a seething layer of quantum activity, a firewall of intense energy or a fuzzball of tangled strings where information is stored and processed. This paradox forces us to see that spacetime and information are not separate concepts. The solidity of geometry and the preservation of data may be two sides of the same coin, a deeper truth about the universe waiting to be uncovered in the shadow of a black hole. Yet our deepest theories of the very small present a paradox that threatens to unravel our entire cosmic story. The vacuum of space is not empty. According to quantum field theory, what we call nothing is in fact a turbulent sea of activity. At the tiniest scales, pairs of virtual particles, a particle and its antiparticle, spontaneously flicker into existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and vanishing back into the void. This is not a rare event. It is a continuous, frantic foam of creation and destruction happening everywhere all the time, in every single cubic centimeter of the universe. This relentless quantum jitter should carry an immense energy density, a property of empty space itself, and according to Einstein's equations, this energy should produce a powerful gravitational repulsion, a cosmological constant that would curve spacetime with unbelievable force. When physicists calculate the expected strength of this repulsion from the quantum vacuum, the number they get is so large it defies reason. It is a number with 120 zeros after it. To put that in perspective, the entire observable universe contains roughly 10 to the power of 80 atoms. This vacuum energy prediction is 10 to the power of 120, a number so vast it is greater than the number of atoms in the universe multiplied by itself. Yet when we measure the actual expansion of the cosmos driven by dark energy, the observed cosmological constant is almost zero. It is there, just enough to push the galaxies apart, but it is a whisper compared to the theoretical scream. Calculated value is 10 to the power of 120 times larger than what we observe. This is not a small error. It is the most spectacular failure of a prediction in the entire history of science. We are not just a little bit wrong, we are wrong by a factor that is essentially infinite. This monumental mismatch is known as the Vacuum Catastrophe. It tells us with brutal clarity that something is profoundly missing from our understanding. Our two most successful theories, quantum mechanics and general relativity, are speaking completely different languages when they describe the nature of nothing. One tells us the vacuum is a seething, energetic foam, while the other observes a cosmos whose empty space is only gently repulsive. Reconciling this chasm is the single greatest challenge for any theory of quantum gravity. The vacuum catastrophe is the silent, gaping hole in the center of modern physics, a constant reminder that the true nature of spacetime's architecture remains hidden in the quietest place of all, the void. This invisible framework of cause and effect is woven directly into the geometry of spacetime itself, At every single point in the cosmos, your entire history and your entire future are mapped out by a simple, elegant structure, your personal light cone. Picture yourself standing in a dark field on a clear night. The light from stars that reached your eyes at this very moment left them years, centuries, or millennia ago. Those stars, at the moments their light departed, are events that lie within your past light cone. They are the only events in all of space-time that could have possibly sent a signal, any signal at all, that could influence you right now. Conversely, any action you take now, any message you send, can only reach events that lie within your future light cone. This is the universe's ultimate speed limit in action. Since nothing can outpace light, no influence, no information, and no cause can travel outside the boundaries of this cone, it is your causal universe, the total extent of reality you can ever interact with. This structure guarantees that every effect must have a cause that lies in its past light cone, preserving the logical order of the cosmos. But this structure is not rigid. The fabric of spacetime is flexible, and its warps can dramatically reshape these cones. Far from any massive object, your light cone points forward in time in a symmetrical, predictable way. But as you approach a black hole, the intense gravity begins to tilt this structure. The fabric of spacetime is flowing inward, like a river rushing toward a waterfall, and it drags the light cones with it. Outside the event horizon, your future still contains possible paths that lead away to safety. But the moment you cross that ultimate boundary, something profound happens. The tilt becomes absolute. Your entire future light cone, every single possible path you can take, points directly toward the singularity at the center. There is no future for you that does not lead there. The concept of moving away ceases to exist because the flow of spacetime itself is now carrying you inward at a speed greater than light. This is not a force pulling you. It is the causal structure of reality reorienting itself, sealing your fate. This geometric rule is what prevents the universe from descending into logical chaos. If you could travel faster than light, you could, in principle, travel back in time. You could enter the past light cone of an event and create a paradox like preventing your own birth. The rigid geometry of the light cone forbids this. It is the cosmic architect's master plan for ensuring that every event connects to another in a consistent, unbreakable chain. The universe is not just a collection of things, but a meticulously woven tapestry of causes and effects, where the very shape of emptiness dictates the story that can be told. That ultimate silence beyond the event horizon echoes the profound quiet at the very beginning of everything. General relativity, our most powerful description of spacetime, takes us on a journey backwards, tracing the expanding cosmos to an ever smaller, hotter, and denser state. The equations lead us inexorably to a single point, a moment of infinite density and temperature, the Big Bang Singularity. Here, the mathematics itself screams in protest. The curvature of spacetime becomes infinite, and our familiar concepts of before and after simply dissolve. According to this pure geometric picture, the universe and the very architecture of spacetime had a definitive beginning, an ultimate starting gun fired from a state that defies all logic. Yet, most physicists see this not as a final answer, but as a glaring sign that our theory is incomplete. An infinite result in physics is often a flag, signaling that we have pushed a good idea beyond its limits. Just as the old classical physics broke down inside the atom, general relativity shatters when confronted with the entire universe compressed to a point. This tells us we are missing the crucial ingredient, a theory of quantum gravity that can describe these most extreme conditions. Without it, the initial singularity is a mystery wrapped in an enigma. To resolve this, some of the most brilliant minds have proposed ways to avoid this cosmic starting line altogether. One of the most elegant ideas is the no-boundary proposal put forward by James Hartle and Stephen Hawking. They asked a revolutionary question: what if the universe has no edge in time, just as the surface of the Earth has no edge in space? Imagine the Earth's North Pole. If you treat it as the beginning of time, all lines of longitude suddenly converge from nothing, which makes no sense. But we know the Earth is simply a smooth, curved surface with no true starting point. Hartle and Hawking applied this logic to the entire cosmos. In their proposal, when we look back to the very earliest moments, the familiar distinction between time and space blurs. Time smoothly transforms into a fourth dimension of space, creating a closed, four-dimensional geometry without a sharp boundary. There is no singular point of creation, no definitive first moment, only a smooth, finite geometry where the universe simply is. In this view, asking what happened before the Big Bang becomes as meaningless as asking what is north of the North Pole. The question of a true beginning remains one of cosmology's deepest frontiers, a puzzle that strikes at the origin of the stage itself. Did spacetime erupt from a singular geometric flaw, or does it form a perfectly self-contained structure with no beginning and no end? The answer will rewrite not just our cosmic history, but our understanding of what it means for reality to exist at all. The elegance of Einstein's equations belies a brutal mathematical complexity. For a single, perfectly still black hole, we can write down an exact solution, a precise description of its silent, frozen geometry. But the real cosmos is a violent and dynamic place, filled with spinning, colliding, and merging objects. To understand these events, we must move beyond pen and paper and into the realm of supercomputers, a field known as numerical relativity. Here, the smooth fabric of spacetime is broken down into a vast, three-dimensional grid of points. The supercomputer then calculates how the curvature at each point evolves over time, solving Einstein's equations step by tiny step across this digital lattice. It is a monumental task requiring millions of hours of processing time to simulate just a few seconds of a cosmic collision. These simulations are our only window into the precise choreography of such events. Before LIGO made its first detection, numerical relativity had already predicted the specific gravitational wave signal that two merging black holes would produce. The now famous chirp sweeping upward in frequency was not a surprise, it was a confirmation of a digital prophecy. These supercomputer models allow us to witness the invisible. We can watch as two black holes in their final moments whirl around each other at nearly the speed of light, churning the space-time around them into a chaotic storm. We see their event horizons stretch and merge, forming a single, wobbling whole that rings down like a bell, settling into its new, quiet shape. These visualizations are not just animations, they are solutions to the universe's most fundamental equations of motion. They reveal the nonlinear, chaotic heart of gravity, where small changes in initial conditions can lead to wildly different outcomes. Numerical relativity is our digital laboratory, a place where we can stress-test general relativity in its most extreme regimes and watch, in awe, as the hidden architecture of reality twists knots and finally smooths itself out once more. The precise values of the universe's fundamental constants feel almost too perfect to be an accident. The strength of gravity, the mass of an electron, the exact energy of the vacuum, each one is set to a value that seems chosen to allow our existence. If the force that binds atomic nuclei were just a fraction weaker, the universe would be a thin soup of hydrogen, with no heavier elements to build planets or people. If gravity were slightly stronger, every star would burn its fuel in a furious flash, collapsing into darkness long before life could ever emerge. It is as if the cosmos was constructed with our presence in mind, a universe that seems to anticipate its own observers. This uncanny alignment is known as the Anthropic Principle, a simple but profound idea. The universe we measure must be compatible with the conscious life that is here to measure it. We could not possibly find ourselves in a cosmos where the constants forbid atoms, stars, or complex chemistry, because in such a barren place there would be no one to ask the question. In a single, lonely universe, this fine-tuning presents a deep mystery, a hint of purpose or design. But within the infinite froth of the multiverse, the mystery dissolves into statistics. If an endless number of cosmic bubbles are constantly budding off, each with a random roll of the physical dice, then every possible combination of constants will be realized somewhere. In the vast majority of these universes, the numbers will be wrong, and those realms will remain dark and empty forever. But by the sheer law of large numbers, a few rare bubbles will, by pure chance, get the numbers just right. We do not live in a special universe, we live in a viable one. We are simply the inhabitants of that one in a gazillion cosmic lottery ticket where the conditions permitted galaxies to form, stars to ignite, and life to eventually gaze back and wonder why. This shifts the entire foundation of our inquiry. We stop asking why the laws of physics are what they are, and start asking a different, more localized question. Why do we find ourselves in this particular part of the multiverse with these specific constants? The answer is now startlingly straightforward, because this is the only kind of neighborhood where beings like us could ever arise. The Anthropic Principle places us firmly within the cosmic landscape, not as its central purpose, but as a fleeting, inevitable consequence of its immensity. Our role shifts from being the intended audience of a finely tuned architecture to being transient observers in one quiet corner of a reality of unimaginable variety, leaving us to ponder what other forms of observation might be happening in the bubbles next door. Our cosmic story does not end with the present expansion. The fate of the entire universe, the ultimate destiny of spacetime itself, hinges on a silent battle between two invisible architects, dark energy and gravity. Today, the evidence points toward a cold and lonely finale known as the Big Freeze or heat death. In this scenario, dark energy's gentle but relentless push continues to accelerate the expansion of space. Billions of years from now, the last stars will flicker out, their fuel exhausted. Galaxies will drift ever farther apart, their light stretched into useless, invisible wavelengths. The cosmos will become a progressively darker and more dilute soup of isolated particles, where the temperature approaches absolute zero and no more work can be done. It is an end not with a bang, but with a fading whisper, a universe reaching a state of maximum entropy where nothing ever happens again. This is the most probable future, a vast and eternal stillness written into the current geometry of our cosmos. Yet other, more violent endings remain possible. What if dark energy is not constant but grows stronger over time? This could lead to a far more dramatic demise, the Big Rip. In this scenario, the repulsive force would eventually overcome every binding force in nature. First, galaxy clusters would be torn asunder, then individual galaxies. As the expansion accelerates to an infinite rate, the fabric of spacetime itself would shred. Stars and planets would be ripped apart, and finally, in the last terrifying fraction of a second, even atoms and atomic nuclei would be torn to pieces. The universe would end in a catastrophic rupture of the very stage upon which reality plays out. Conversely, an older idea imagined a different finale, the Big Crunch. This would require the density of matter and energy to be high enough for gravity to eventually halt and reverse the expansion. The universe would begin to contract, slowly at first, then with increasing speed. Galaxies would merge in a blue shifted blaze, the background radiation would heat up, and eventually, all matter and energy would be compressed back into a searingly hot, ultra-dense state, perhaps triggering a new Big Bang. While this cyclical universe is a compelling idea, our measurements of the cosmos make it unlikely. There simply does not appear to be enough matter and energy to overcome the repulsive push of dark energy. The ultimate fate is a cosmic tug-of-war, a calculation based on the precise energy density of dark energy, matter, and radiation. For now, the data points to a cold, expanding eternity. But the final chapter of Spacetime's story is still being written, its conclusion hidden in the mysterious nature of the dark energy that commands the cosmos. Every prediction of general relativity has been confirmed, but the quest is far from over. Scientists are now pushing the instruments to their absolute limits, searching for the tiniest crack in Einstein's elegant edifice. The Event Horizon Telescope, a planet-sized array of radio observatories, delivered our first ghostly image of a black hole's shadow. That dark circle, silhouetted against a whirlpool of light, is not the event horizon itself, but the point of no return for photons, a profound test of gravity in its most extreme environment. It is a direct snapshot of spacetime warped to its breaking point. Soon, a new kind of observatory will take to the void. The Laser Interferometer Space Antenna, or LISA, will consist of 3 spacecraft flying in a perfect triangle millions of kilometers apart. Freed from the seismic rumble of Earth, it will listen for the low-frequency hum of the cosmos, the deep thrum of supermassive black holes merging at the hearts of galaxies. These are collisions that shake the very foundations of spacetime, and LISA will hear them with a clarity we can only dream of today. Even more precise tests are probing the very core of the theory, the Equivalence Principle. This is the idea that all objects fall at the same rate in a gravitational field, that there is no difference between being in an accelerating rocket and standing on a planet. It is the bedrock upon which general relativity is built. Experiments are now testing this principle with astonishing sensitivity. Imagine 2 small cylinders made of different materials like platinum and titanium orbiting Earth inside a satellite. If one falls even slightly faster than the other by a fraction of a trillionth of a percent, it would shatter our current understanding of gravity. Atomic clocks, those exquisitely precise timekeepers, are also being sent into orbit. By comparing their ticks with clocks on Earth, we can measure the minuscule time dilation caused by our planet's gravity with unprecedented accuracy. A deviation of even 1 part in a quintillion would be a signal, a whisper from a deeper layer of reality. Finding any crack in this century-old foundation would not be a failure, but a triumph. It would be our first glimpse of the new physics that must lie beyond Einstein's universe, the hidden blueprint for the cosmos we have only just begun to explore. The solid stage beneath our feet, the vast emptiness between stars, might be the universe's grandest illusion. We have traced the subtle warps and ripples in spacetime, treating it as the fundamental canvas of reality. Yet the most radical frontier of physics suggests the opposite, that this canvas is not fundamental at all. Spacetime may be a secondary effect, a collective behavior that emerges from a more primitive, non-geometric reality. Think of a calm lake. Its surface appears as a continuous, solid plane, perfect for reflecting light and carrying waves, but we know this is a large-scale illusion. Zoom in close enough and you find a frenetic dance of countless water molecules. The smoothness of the lake is not a fundamental property, it is an emergent one, a consequence of trillions of parts interacting. In the same way, the smooth, 4-dimensional continuum of general relativity with its elegant curves may be a similar kind of average. It is the macroscopic calm that emerges from a microscopic storm we cannot yet see. The holographic principle we explored earlier is a powerful clue pointing in this direction. If a three-dimensional universe can be fully described by information encoded on a two-dimensional boundary, then our direct experience of three-dimensional space cannot be the most basic layer of reality. The solidity and extension we perceive are projections, a rendering of a deeper computational process. This shifts the entire goal of quantum gravity. The quest is no longer to quantize the gravitational field as if it were just another force. Instead, the mission is to discover the fundamental ingredients, the atoms of reality, from which the very concepts of space and time naturally crystallize. What could these ingredients be? One compelling candidate is quantum entanglement. This strange connection where the state of one particle instantly influences another across vast distances was once derided by Einstein as spooky action at a distance. But it may be the very glue that binds space together. Imagine space not as a pre-existing container, but as a network of relationships. Where two quantum particles are deeply entangled, a fundamental link is forged. Weave a vast, dense web of these entangled links, and the property of spatial proximity itself begins to emerge. In this view, the distance between two objects is not a primary measurement. It is a measure of how entangled they are. Two highly entangled particles are, in effect, close together in space, even if they appear physically separated. This suggests that the hidden architecture we have been exploring, the fabric that bends and ripples, is itself a tapestry woven from threads of quantum information. The force of gravity would then not be a fundamental interaction, but a thermodynamic force, an entropic effect that arises as the system seeks equilibrium, much like the pressure in a gas emerges from the collective motion of molecules. This would mean that at the Planck scale, the universe is not a tiny, curled-up ball of extra dimensions. It is a realm without space or time as we know them, a vast, interconnected network of quantum data. The Big Bang Singularity would mark the moment this network crystallized into the geometric reality we recognize. We are left with a staggering implication. The universe is not in space and time. Space and time are in the universe, emergent properties of a deeper, more mysterious existence. The true nature of reality may be a cosmic computation, and we are living inside its most magnificent and tangible output. This hidden architecture is not a distant abstraction. It is the very ground of our being. Our journey has revealed a cosmos where space-time is the ultimate active participant, a dynamic fabric that breathes, warps, and ripples. From the gentle curve that guides a planet in its orbit to the violent puncture of a black hole and the mysterious, repulsive push of dark energy, this geometry is the silent author of reality. We have witnessed the intimate dialogue where matter and energy command the fabric to curve, and that curved stage, in turn, dictates the motion of every particle, the path of every light beam, and the relentless forward flow of time. Profound mysteries still linger in the shadows, from the true nature of dark matter and the quantum origins of gravity to the ultimate question of the universe's first moment. Yet each new discovery, whether a faint chirp from colliding black holes or a ghostly image of a cosmic shadow, pulls back another layer of the veil. The most profound realization is this: you are not a passive spectator living on a fixed stage. You are an inseparable part of this ever-evolving fabric, a conscious expression of the universe's own hidden architecture. If this exploration has shifted your perception of reality, share your thoughts in the comments and subscribe for more journeys into the deepest mysteries of the